this lecture. Okay. I think last week we are here. Okay, so this is so as I said last time, we have to okay. As I said last time, we have two types of stress. We have two types of stress. First is normal stress, written as sigma equal to F over A, and shear stress, written as tau equal to F over A. So the difference only in terms of the direction. The direction of normal stress, the force is perpendicular. Perpendicular to the area, and for shear stress, the force is parallel to the area. So this case is the case of normal stress, this one, because this is the area or this one lah, same. This one and this one is the same area. So this is the force, and for parallel, the area is for the shear stress, the area is parallel to the force. We will look into the shear stress later. Okay, but what I want to explain today is about what happened when you pull your object. This is your rigid body. This is your object. But then your object will fail making a plane in this with a certain amount of angle. You know what I mean? So when you have this object, and then your object fail making an angle like this, so it will provide an angle like this. You know what I mean? This is theta. So what happened to your equation or formula? Because we know that stress is equal to F over A. So when this thing happen, when the force that you apply making an angle like this, what happened to this equation? What happened to this equation? Because the area has changed. Okay, so this is what happened to the equation. Stress is equal to F over A original cos square theta. And for the case of shear stress, tau is equal to force over A original sin theta cos theta. So it's not the same as this anymore. Faham tak? So how this equation occur lah? How this change occur? So let's have a look. Okay, so when you have an object like this, so when you pull here, or F or P lah, P, we use P here. So stress equal to P over A, because the area is perpendicular to the force, like this. This is your P, this is your area. So it makes 90 degree. Because cos 90 equal to 1. Betul ke? Sekejap
Bukan saya, cos 90 equal to 0.
Apa yang equal to 1?
Sin 90.
Sin 90?
Ya.
Saya tak kerti lah tekan calculator ni. Sekejap tekan calculator pun tak kerti. Dulu saya belajar tak pakai calculator tau. Dalam zaman saya SPM tak pakai calculator. Okay, tak apalah. So basically, so you know this rule. So stress equal to P over A when area and force is 90 degree. When it 90 degree, or we say it as a perpendicular lah. So when this thing happen, so it make an oblique plane like this. So this is oblique plane. Oblique plane is tilted plane. Tilted ni condong condong. Okay, and then okay, so this is the area, and this is the theta. This is the theta. Okay, this theta actually, if you draw like this, so this is the theta. So if this is F, which is F is perpendicular to the new area, so this theta is actually equal to here. Faham tak? So this theta and this theta is actually the same.
Tahu.
Okay, so this P has become the new P, will become the new P lah. So this F is equal to, so this, if this is F, so if this is 90 degree, okay, this is P. So P cos theta sin theta. Okay, so cos theta equal to F over P. This one. Cos theta equal to F over P. So you will get F equal to P cos theta. Faham tak ini?
Faham?
Faham Tak faham cakap If tak faham cakap tau.
Okay.
Okay, so this is for normal stress. This is for normal stress. So in the case of, this is, okay, we write here, this is a normal stress. In the case of shear stress, so shear stress happen when force and area is parallel. So parallel means the force should be in, if the area is here, if the area is here, this is the area, that means the direction of the force should be parallel to the area. So that means this is the direction of the force. If normal, the direction should be here, which is F, this one, or this one. So it makes 90 degree. If it is shear, the force should be in this direction. So it is in this direction, or this direction, or this direction. So either way lah. So in this case, this slide write the shear force as V. Okay, the normal force, it is written as F. But for the shear stress, the shear force is written as V. Okay. So this V, this direction actually same to this direction. But this one and this one is the same. So if this is V, okay, so this one, this V and this is the same lah as V. So sin theta equal to V over P. So you will get V equal to P sin theta. So this is case for shear stress. Faham? So the new, so if in the normal case, if it is not tilted, the equation for the normal stress is stress equal to F over A, in which that A is we can say that this A is A original lah. Okay, A original. But when it is tilted or in an oblique plane, this A has changed. This A has changed in which that the F is this. Okay, so F is equal to P cos theta. So this is the new F because you change this. And then this A naught, is equal to, so this is your A original, this one, and this is your A new. This A new is A theta, this one. Faham tak? Because if you want to draw, you can draw like this. This is your new A theta, and at the back, this is your A original. Okay, this is your A original. So this makes an angle which is theta, and this is 90 degree. Okay, here, and this one and this one is actually the same lah. So this is 90 degree, and this is your theta. So your A naught, A original, equal to, so if you change, so in order to get the or this one is when it is tilted, it's equal to F over A theta actually. A theta, this one A theta. So A theta is equal to, so if you make cos theta is equal to A original over A theta. So A theta, you get A naught over cos theta. So this one, A theta is equal to A original over cos theta. So if you simplify, you will get is equal to P over A original cos square theta. Faham tak?
Faham.
Siapa tak faham boleh tanya So that's why you got this. You must know why this becoming this, and you must know why this becoming this. So this one is from here, and this A theta, as I explained, this is your A theta. This is your A original. So this makes a 90 degree, and this is your theta. Okay. So what is A theta? A theta, A theta is what? A theta is what? So in order to get A theta is what, you have to do cos theta equal to A original over A theta. So A theta equal to A original over cos theta. So that is why you got this becoming this. Okay. Similarly, for the case of shear stress, tau is equal to V over A theta. When it is tilted lah. So if you draw this is your A theta, and this is your A original. Okay, this is 90 degree. So this is your A original. This is your A theta. And your theta is here. So V is here lah. And A theta is the same. A theta is the same as we have calculated for the normal stress, in which that A theta equal to A original over cos theta. So we change V with P sin theta over A theta equal to A original over cos theta equal to P over A original sin theta cos theta. Faham tak?
Faham.
Faham So that is why you got this. And then this one is the normal stress. This one is the normal stress. This one is the shear stress. This is shear stress. So that's the maximum stress occurs when the reference plane is perpendicular to the member of axis. So when it is perpendicular, the stress is maximum for normal stress. Okay, the stress is maximum. The shear stress will be 0. Okay, when it is parallel, which is 0 degree, the maximum shear stress occur, and the normal stress 0. Okay. The maximum shear stress occur for a plane with respect to the axis. Oh no, my mistake. The maximum shear stress occur for a plane at plus minus 45 with respect to the axis. So the maximum shear stress occur when it is 45 degree. I think sine 45 times cos 45 is the same. That's supposed to be right. Sine 45 times sine
45 cos 45 sama kan?
apa dia?
Sin 45 dengan cos 45 tu nombor yang sama.
Kan? Sine 45 cos 45.
Punca 2/2.
Apa jawapan dia?
Punca 2/2.
Ada 80.
Ataupun kalau nombor puluhan dia akan jadi 0.707.
Apa betul Jok?
0707.
0707. Kita rasa saya.
Kalau dia darab sekali dengan cos 45, dia akan jadi 1/2.
Saya tak reti lagi untuk calculator. Tapi kemarin tak apa, nanti saya tanya anak saudara saya nak tekan calculator. Okey. Tapi okey, tak kisahlah, yang penting awak faham. Okey, konsep dia.
Saya nak tanya. Yang maximum normal stress tu, dia kata reference plane is perpendicular to the member axis. Member axis tu apa?
Reference plane, ni reference plane. Ni reference plane. Maksudnya plane tu satah.
Okay.
Plane tu satah, reference tu rujukan. So maksudnya satah rujukan tu maksudnya inilah dia area tu. Maksudnya area lah ni, benda ni maksudnya area. Okey, member axis ni ialah ni lah. Axis aksi.
Faham. Okay,
Okay, ni if in case under general loading, ni tak payahlah Ni tak payah. We actually, so when you have a multiple direction of stress in three axis, so this is the condition lah. Tapi ni tak payahlah. Okay, factor of safety. Okay, factor of safety is a unit in which that it will describe is a unit to represent the value of a tolerance. The value of a tolerance. For example, you have a lift. You go to shopping mall. For example, you go to shopping mall. This lift says that the maximum people can go inside the lift at one time only 10 people. Okay, 10 people. So this is the allowable I think this is the allowable stress. This is the allowable load. Okay, but actually this cable can go up to 20 people. But for the safety, we will not say that the maximum people can go inside the lift up to 20 people, because if you put 22 people, this cable will fail. So we only display that the maximum number of people can go inside the lift only 10. Faham tak cakap apa? So this could be ultimate load. So the factor of safety is equal to 20 over 10. Is equal to 2.
Jadi nilai factor safety ni kena lagi besar, kena lagi kecil tak?
Lagi besar lah.
Lagi besar selamat lah.
Lagi besar lagi selamat. Sebab katalah awak masuk lift, lift tu kata 10 orang je maksimum. Tapi sebenarnya in reality secara teori yang boleh maksimum sebenarnya 20. Tapi sebab kalau kita cakap 20, nanti awak isi terlebih 21 22 orang. Awak faham tak? So kalau awak isi 21 22, lift tu akan putus. Tali tu akan putus. So in order nak selamat, kita akan tipu. Kita cakap bukan 20 tapi 10 je. Faham tak cakap apa?
Faham.
Faham That is factor of safety. That means tolerance lah. Tolerance in which that we want to make sure that the cable not to fail. So we put this tolerance. So why factor of safety? Why you need to put the tolerance? Why it should be considered? Because the material properties is uncertain. Okay, even though we know that properties, material has its own properties, we know the value of that material, but it is still subjected to environment. Sometimes material degrade fast. Material degrade faster in depending on the environment. Okay, if the environment is corrosive, then the material will degrade faster. If the environment is not really corrosive, the material will last longer. Faham tak? And then uncertainty of loading, uncertainty of analysis, number of loading cycle. Ni lah semua ni logik-logik je. Faham tak? Nak saya explain tak benda ni?
Faham saya.
Ni uncertainty of loading ni sometimes kadang-kadang macam kita cakap maksimum 10, tapi ada orang diletak mungkin 12 orang macam tu. So some people will put more than the number allowed. Faham tak? More than the number allowed. So we do not know. So that's why we put factor of safety in consideration when we build something. As an engineer, you have to apply this. So similarly, when let's say Boeing or Airbus inventing an aeroplane, so the Airbus A380 for example, so the initial passenger can go inside the A380 is actually 800 passengers up to. But for the factor of safety, it has been instructed that A380, the maximum passenger can go up to only 550 passengers only. Because we want to make sure that it is not too heavy. It's not too heavy for the A380 to fly. Okay. And then uncertainty of analysis, number of loading cycle. Uncertainty of analysis mean even though as an engineer, perhaps sometimes you may make a mistake in your analysis. Okay. So and then number of loading cycle. Loading cycle mean loading cycle mean the repetition of that thing to be used. For example, like this leaf. So this leaf will be used for how long? 20 years, 30 years. Within these 20, 30 years, how many times the repetition, the leaf will move up and down. So, and during the moving up and down, how many load it will carry each time it moves. So this has to be included in the so this is what it means by loading cycle. They mean the repetition of use. So this has to be included in the consideration lah. Sometimes perhaps maybe in 20 or 30 years there are maybe 100 times that people go inside the lift more than 10 people. Faham tak? So sometimes it goes beyond the limit that we have set. And then types of failure as well, maintenance requirement and deterioration effects, importance of integrity of procedure, risk to life and property. Risk to life and property ni risiko lah, risiko because we don't want to lose human being, we don't want to kill people, so we put factor of safety in consideration. Perform to the doing the interval, you should remember can this so maybe if you want to solve this problem, you can try. Let me check if I haven't. So if you want to this problem is actually the same problem that we have looked in the previous example, the one that have rod and beam. This is 30 kilonewton load. This is rod. This is beam. So this rod diameter is 20 mm, and the allowable this one should be here. So the allowable stress for steel is 165 MPa. For example, based on cost, I think we already solved this problem. Yes, this we already solved this problem. And then change with aluminium, 100 MPa. So what is the question? Yeah, we already solved this problem. Faham tak? Faham tak saya cakap apa? Faham tak kalau bila saya kata we already solved this problem? So dia tanya, the question asks you, can the structure safely support the 30 kilonewton load? So you have this rod, and the diameter is 20 mm. This is made from steel, steel in which that the allowable stress of steel is equal to 165 MPa. And this is 30 kilonewton. And the FBC apa? FBC berapa Ingat tak FBC berapa? 40 ke 50? How much is FBC?
50.
50. Okay. So the question asks you what is the value of, okay, so FBC is 50 kilonewton. So to solve this problem, you have to find stress is equal to F over A. So F is 50 kilonewton, A is equal to pi r square. So this is D, R is equal to 10 mm. So R is equal to 10 mm. 10 mm is equal to 10 times 10 to the power of minus 3. Okay. So you change this pi times R. R is 10 times 10 to the power of minus 3 R square M. Faham tak? So you will get this value. You will get this value and you see how much is this value. So if this value is larger than this value, that means the rod cannot support 30 kilonewton. If this value is lower than this value, the structure can support the 30 kilonewton. So let's see what the calculation shows. We already calculated this one, yeah?
159.
159. So 159, that means it is 8. This one, Sini ke? Sekejap. Saya pun pening. Yes, this one. Okay, this one, 159. So this 159 is lower than 165. That means this 30 kilonewton is safe. So this diameter can be safe to be used. Okay, but because of, and then the question asks you, for reason based on cost, aluminium is better to be used. To change, we don't want to use steel because steel is expensive and higher load. I mean, the weight is quite high, so they want to change with aluminium. However, the aluminium allowable stress is lower than steel, which is only 100 MPa. Okay, this is rod. This is your weight, 30 kilonewton. Previously, your diameter is 20 mm, but now you change to aluminium, but the aluminium only 100 MPa. So what is the diameter of BC that is required when you want to change to aluminium? So you change this equation, stress equal to F BC over area of BC. FBC is equal to 50 kilonewton. Okay, 50 kilonewton. Tak apalah, sini lah. So this one is change to this one lah. 100 MPa, and this one is FBC. You already know it's equal to 50 kilonewton, and this area is equal to pi r square. So this is what you want to find here in this what we call this, in this question. So you got r equal to 50 times 10 to the power of 3 Newton over 100 times 10 to the power of 6 PA times pi, and then set. You will get the value of r. And then when you get the value of r, you times the diameter is equal to r times 2. You will get something. Faham tak? So in this case,
25 je.
25.2.
Memang penting.
Jadi aluminium, you get 25.2. But this is the limit. So in order to be safe, you need a little bit higher value. So they round up as 26. Faham tak? So in the exam, for example, if you didn't write 26, you only show up to this answer, you only lose 1 mark only. Let's say if the total mark is 25, you show all these steps, but you didn't say that it is 26. The maximum marks that you will get is 24 only. You only lose 1 mark. Faham tak?
Faham je?
Nah, because it has to be logic lah. It has to be logic. Okay, any question? We already finished first chapter, which is just the introduction. Let's see chapter 2. Maybe we can have a break for about 17 minutes. So we continue at 1:30. Okay, we continue at 1:30.
Okey je.
Hello.
Two.
Yes, sir.
Okay. Stress and strain exhaloding. This is just introduction. Okay. This exhaloding. For exhaloding, this is also exhaloding lah. So when it is perpendicular to the area. So in this case, this is rod. So rod, this it is can be draw like this. This is P, and this is the area. Okay. So the stress can be written as P over A or F over A. Okay, and you know that strain is equal to length final over length original over length original. Okay, or it can be written as this one as a delta. That means the perubahan, the changes, equal to delta over L original. Or you don't want to write original, also fine. So this one is written as this one. Strain is equal to LF over LF minus L original over L original, or LF is also equal to LF minus L original is also equal to delta. Okay, this is delta over L. So this is the equation for strain. Faham tak? I think I'm not sure if you have met this equation before, but I think you are. I think you have met this equation before. So if the area is 2 times larger than this area, if the area is 2 times larger than this area, so the stress is still the same. Right? The stress is still the same with 2 times higher pressure or forces. So the stress is still the same, and the strain is also still the same. Okay. Similarly, if the length is 2 times longer than the original length, the stress is also still the same and the strain is still the same. This is a stress strain test. In stress strain test, you will have a machine like this. This part is movable. It goes up, and it can go down as well. And this one is fixed. So in this stress strain curve, the result will be presented in a graph of stress and strain. So you will get a graph in this format. Okay, this is the strain gauge. So this so it is not so this should be learned in engineering material or material science. I'm not sure. I think maybe last year or last semester. Last semester, I think. And this when you do the stress strain test, this is what you will get lah. This is stress, and this is strain. Okay, this is strain. It is written like this. So when it fails, it can fail like this, and this is what it will exhibit. So this is the elastic region. And then passing the yield point, this is yield point. This is the plastic region. Okay, in the elastic region from here to here, when you release load, the specimen will return to its original dimension. But passing the yield point, once you release the load, the specimen will not return to its original dimension because the deformation is permanent. Okay, this rupture or this fracture occur here. This rupture occur here, and this point is known as the ultimate tension stress, ultimate tension stress or ultimate tensile stress. Okay, or it is written as ni lah, ultimate stress lah. Here, this one lah. Okay, this is yield point. So this is low carbon steel, and this is aluminum alloy. So similar, strain as elastic region, and then this one is plastic region and the rupture. And this is stress 0.2. This is brittle material. This is ductile material. This is ductile material for low carbon steel and also aluminum alloy. This is for brittle material. For brittle material, the fracture surface will be like this lah, typically flat. There is no necking. Okay, if brittle, if ductile have necking like this. It is like your neck lah, neck. So it will be small. It will be small before it fail. So this is small. But for brittle material, it is straight, not small. You know, like glasses, eh? And then the rupture, the brittle material does not have curve. Does not have curve like this. No curve like this. Only this one. So this one, yeah. This is brittle material. Okay, this is Young modulus. So Young modulus is written as E. Okay, so here, this is, as I said, this is elastic region. This is elastic region. Okay, this elastic region is where the Hooke law occur. Hooke law occur in this elastic region, in which that Hooke law says the stress is directly proportionate to the strain. The stress is directly proportionate to the strain. And when we divide stress over strain, we will have a ratio in which that the ratio is known as elastic modulus or modulus of elasticity. So elastic modulus is equal to stress over strain. Faham tak? Cakap apa? So this is the region of the elastic. This is region elastic region in which that Hooke law is applied. Hooke law is applied. Over strain, it is equal to elastic modulus. And we divide a stress over strain, we will get one value in which that value is known as elastic modulus or Young modulus. Okay, so this is stress over strain equal to E lah, or stress equal to E times epsilon. Okay, faham tak? This is plastic behavior. Okay, as I said before, if brittle material, for example glasses, when you do the stress strain test like tensile test, you will not have a curve. A curve. Your sample will just feel like this. Okay, so this means that your sample is not elastic. Okay, it's not elastic. It is brittle. Okay, so if your sample but this is elastic region. This is elastic region of the sample. When I say that the brittle material is not elastic, means it will not be able, it is not capable, or it does not have the ability to return to original dimension once you give force. So once you try to deform them, they will abruptly fail. Faham tak? So when you have a material which is elastic, when you do the stress strain curve, the stress strain curve will make a curve like this. So this region in which that when it is passing through the yield point, this region is known as plastic. So plastic region means permanent deformation, or plastic is the opposite of elastic. Plastic region is the opposite of elastic. So from this graph, okay, this is the yield point. This is the yield point or the yield stress. So when it passing through the yield point, it is actually, so this is elastic region. This is plastic region. So when it is passing through the yield point, when at B, this is B, and then when it reach C point and you release the load, the specimen will try to return to its original dimension. However, there are some parts of the specimen which already plastic, I mean has been permanently deformed. So the specimen will not completely return to its original dimension. There are some amounts of plastic deformation already occur. So this is known as the plastic deformation lah, plastic deformation. So if you continue doing the test, so finally the specimen will fill lah. This is fatigue graph. Fatigue graph. This graph is to show you the elastic limit. Okay, fatigue is a test to evaluate how many repetition of load can be applied to a certain specimen. Okay, the fatigue test will give a result in the form of SN diagram. So previously, this stress strain curve, like for example tensile test, when you do the test, the graph will be shown in terms of stress over strain curve. This is stress, this is strain. But for fatigue, it will give you the result in the form of stress, which is typically written as S, and also N. N means number of cycle. So that's why it is SN graph. This is stress. This is number of cycle. I think it's already 1:50. We continue the lecture on tomorrow. Okay.
Okay, sir.
Okay, have a good day. We continue tomorrow.
Okay, thank you.
Thank you, sir.
Thank you.